Okay, so I think we're ready to start. All right, so this lecture has this long title here. That's because it's part of a series of lectures, these theoretical and methodological foundations here that are university-wide or at least like computer science-wide. And then there's different series like computer vision or whatever, like different things here. So definitely we are trying to have this kind of enforced focus on autonomous systems. Actually, the name that has been used in the past is mathematics for intelligent systems. So I will explain what I understand by autonomous systems. But initially the lecture was started by Nathan and Mark. So Mark Toussaint was a professor at the university. So I'm actually the interim professor for Mark Toussaint because he moved to the Technical University of Berlin. And Nathan was a research scientist in his group part-time for I think 1 year. And he gave initially the Mathematics for Intelligent System lecture, which is this. And so I did this. This is the third time that I do this. And I based off most of the lectures of a book that you can find here. The PDF is online. And we depart from the book for 2 lectures. At least last year. This year, I think we will do 3 lectures, or 3 or 4 lectures. So there's a lecture at the end, which kind of wraps up with examples of applying mathematics in the context of intelligent systems. And this is usually given by the TAs. And they are kind of like showing you what they do in their research, how they do apply mathematics in their own research. It goes really fast because they only have an hour and a half and they're 3, so. Most of the lectures are going to be based off this book. I would highly recommend that you first download, that's easy, but maybe print it. We have at the university, for example, the Erasmus students who don't know, we have a printing system. It's a kind of workshop, and you can, I think, either print beforehand and then get it like nicely as a book or something like that. So this is completely allowed by the authors here. Yeah. Okay, so first I'm going to talk a little bit about the Elias context and kind of how we do the grading, how is the exam going to happen, and so on. And today I'm going to introduce a little bit the context of mathematics, like kind of give an overview of mathematics in general, and then tell you what we are really going to focus on in this class, because of course the idea of this class is basically that most of you guys are computer science students, and maybe you can show of hands who is in computer science. Well, okay, so most of you is not most of you, it's like, so where are the others from? Electrical engineering, so infotech. How many of you? Automation. Okay. Are there some students from kybernetics? No. Okay. Yes, so the focus is basically to level everybody in the masters. Are you all from the masters? Are there some people from the bachelor's program? No. So everybody's in the master. So the idea of this course is to level everybody who's in the computer science masters so that they can do kind of research in AI. That's kind of the idea, so that you can, so the focus is machine learning, robotics, these kinds of things. What is the mathematical background that's needed for this type of things? And so that everybody's kind of, because oftentimes in computer science, you see some discrete math, you don't see continuous optimization, you don't see derivatives, and then, or you have a too little understanding of linear algebra or things like that. So we kind of level everybody. That's the idea of this course. And at the end, I will show, in these example sections, I will show 3 things where the content of this course is going to be applied. It might be things that you don't really understand, but that's the idea because it will tell you, okay, that's where we're going. That's what you will understand pretty well at the end. This thing is not working. Okay, so I shouldn't be too far. All right, so who is going to be teaching this course? Me, and that's my email, but I would recommend that you don't use it so much. The other people who are helping or teaching this course are the TAs, and that's how you contact them. So there's a single email. I'm actually CC'd on this email, so if you use both, I get the emails twice, and then I really don't get happy at all. So these are the TAs. So mainly it's Philip who's here. There will be Yannick supporting, and Eugene not so much, because she already is teaching another course, which is the Practical Robotics. I don't know if some of you are in there. Maybe not. So the preferred way of contacting us, as I said in the beginning, is through the Elias forum. And that's because then you broadcast to everybody else, and it's informative for everyone. So we will make announcement, kind of like permanent announcement, available from the web, so that you can easily check that on your phone or whatever thing, and it's maybe easier. Well, it's easier to access than the Elias forum in general. And the Elias course materials, so the videos, the exercise sheets, the slides, and so on, they will all be on Elias, including this lecture right now. What will not be on Elias is the exercises, which will be on WebEx. Actually, we don't have that in the slides. So when do things happen? So the lectures are now, and here, and well, for those of you who are seeing this online, the time is Tuesday mornings, 9:45, and the room is 3801 in the informatics building. 38 is for the street number, and the street is Universitätsstraße. And it's a big hall, so there's a lot of space. So hopefully you have enough distances. But you have to wear a mask if you come in presence. I mean, I'm just saying this for the people online. Okay, so the tutorials, no, we do that's fine. So we do not do the tutorial on WebEx. We will do the same, right? We will record the tutorials, I guess. No? We're not allowed. Yeah. So that's annoying. So that's part of the policy of the kind of pushing to presence, is that the lectures should be accessible. How do they say that? Like offline, so that you don't have to be here, right? But for the tutorials, we are pushing you guys to come to the university. So, I mean, I didn't decide that, but I mean, the university policy is that we are trying to go back to presence. So Thursday mornings, that's kind of a requirement, and I will say about how much you have to be at the tutorials. I would say if you really want a nice grade, you have to do all the tutorials in presence. And the room, so it's Thursday morning, same time, and the room is 03, which is on the other side of the hall. Okay, so coming to the exercise procedure, we have a weekly exercise sheet. Exercises are solved at home, so you have to work on them on your own. But okay, so that's the complicated part. So the idea is that you go on Elias, we have a voting system, and you vote for the exercises that you want to solve that week, because you don't have to solve all the exercises through the semester. And during the tutorial session, You will be randomly selected if you have voted for this exercise. So if you vote, you do have really to come there. Then you're randomly selected to present your solution to the exercise. And that's the requirement, is that you have to have 50% of the, you have to have voted for 50% of the exercises that are proposed during the semester, such that you can get the shine. But you also have to at least present one exercise to get the shine. So it's not only that you have to vote for 50% of the exercise, so by voting you're explicitly saying, okay, I'm ready to present the exercise if you pick me randomly, right? But then you also need to be selected randomly once. And we will make sure that this pseudo-random sampling happens and that you are selected at least once. Then you get what is called in German the shine, which is simply saying that you're allowed to participate in the exam. Okay? You cannot participate in the exam without that. That's just saying that you have to have done actively the exercise sessions in some way. We do not grade the exercises. It's just we want you to do them, and that's kind of our way to enforce that everybody tries to solve the exercises, at least 50% of them. And that you kind of show up to the present lecture minimally, right? So I would say if you kind of have to participate to 50% of the sessions, so there's like 10 sessions or something like that. You have to come physically to the university for this course, I would say 5 times, so that you can pass be allowed to pass the exam. Okay, so the first exercise sheet will be available on the 28th, which is in 2 weeks. And yeah, so the exercises are mostly, math exercises that you do on paper, but there are also some programming exercises, very few, I think. Okay, so yeah, so the university wants us to name that course Theoretical Methodological Foundations of Autonomous Systems. So let's just answer that question. What is an autonomous system? So my definition is that it's a system that takes decisions. So yeah, so it might be an agent, a computer program, maybe even an electrical kind of or electronical device that takes decisions, and that basically can modify itself, its state. So I take a decision to switch some state variable, that's an internal thing, or modify the environment. So if I'm like a device that, for example, a typical thing that's shown in control is you're monitoring the temperature of a room, you are this agent, and you have one temperature sensor, and you can blow hot air or whatever, and then the decisions that you might take might be, by reading the sensor, kind of have some internal representation of how warm the room is, and then your actuator might just be, I turn on and off the air blowing, hot air blowing device, whatever. So that would be some basic intelligent system, and then learn from its interaction with the environment, which means that you change the way you respond to change kind of over time. I would say these kind of 3 components make an intelligent system, or and again, so autonomous system is a broad term. Here we are like focusing more actually on intelligent systems. So our lab works on robotics, and so I took this example of the temperature controlling device system. But if you look at the traditional control pipeline that interacts with an environment, usually what you have is a state estimation pipeline. And at the end, we'll see the Kalman filter, which is the most basic state filter with a lot of assumptions. So the dynamics are, you have to wake up. The dynamics are linear, and the assumption on the distribution that you're getting in is Gaussian. So it has a mean and covariance. And your observation system is also linear. So it's like the observation comes here, right? So that's O for observation. It's written here. Okay, so that's for the state estimation system. Then you make a vectorized representation of whatever is in the environment. So here it includes the interacting human. And then you control the robot by reasoning on that state and outputting an action. And that optimal controller can usually be thought of simply as a policy. So that maps states to actions, control policy. So that basic divide is also the divide that I would say is kind of the divide of an intelligent agent, something that builds a state representation, maps that state to an action, and loops with the environment. Okay, so, I wanted to give an example that fits really well to Stuttgart. So the example of a car. So there's, when we drive a car, the actuation is the steering angle, which is a scalar, and the accelerator, which is another scalar. You might say, so the accelerator directly acts on the second order derivative of the position, which is what is written here. And the steering angle is the first order derivative of the actual angle of the wheels. And so I'm of course talking about an autonomous system. So it's a system that's able to build its own state representation and then have its own policy. And it does that by having many sensors. So this is just what I could come up with as an incomplete list of sensors that the car might have. And so then the state is the angle of the wheels, theta, the speed of the car, which is the first order derivative of the state, of the position, sorry. The location in the world. So location is a different word than position, in the sense that when we say location, usually we also imply the orientation of the vehicle. And then the location of pedestrian or other cars, and this is what's depicted here. So this is one of the early things that came out of what is now Waymo, okay? So I think this picture dates back from like 2012 or something like that. And so this is like a cyclist and a bounding box around that cyclist, and you can see that there's a color coding that makes the cars a different colors as the pedestrians. So already back then they could kind of fit bounding boxes to the things in the environment based on the LiDAR data, and identify the pedestrians and the cars and so on. So how can we reason about an autonomous system? If you Google autonomous systems, of course, you're going to land on this, which is what mathematicians consider an autonomous system, which is an autonomous system of ordinary differential equations which do not depend on time. So there the system word is simply for system of equations, okay? And autonomous means that, the behavior it does not depend on time. So that's what it means. And the state X is usually thought of as a vector in n-dimensional Euclidean space. And so this definition of what would an autonomous system be is like super restrictive. And the definition sometimes but the definition sometimes does match our modern understanding of a autonomous system. So I said an autonomous system, in my definition, is some kind of loop with the environment. It's building up a state representation and then acting based on that state representation that it has of its environment, including itself. So what we have here, x is actually, could be considered as a state variable, and f would be the policy, right? And so that does kind of match what an autonomous system, in my definition, can be sometimes. And the idea is that so there's a kind of there's a direct mapping between autonomous system of differential equations and dynamical systems. And the idea is that many of the autonomous systems that we find, or intelligent systems that we find, can be represented as dynamical systems. So that's kind of the connection there. But the key idea is just that mathematics allows us to formally reason about systems. And if I can represent my autonomous systems as an autonomous system of differential equations, then that's like I can do a lot of things based on all the mathematics that's been developed for reasoning about differential equations. And the kind of process that goes into reasoning about autonomous systems in general is to define how the system works and then make a bunch of proofs based on logic and deduction and kind of reasoning, and that will lead to guarantees about how the system works. So this process of going from definition to guarantees of how, like strong guarantees about how the system works, is really at the heart of Kybernetics. So nobody from Kybernetics is here but, today. But the idea is that their reasoning in terms of systems and control leads to these strong guarantees. So usually they study kind of simpler systems than what we do in computer science, because we build this crazy stuff and we are really struggling with having guarantees with them, whereas they kind of always try to guarantee the system of the behavior of the system, and thus kind of are limited into the scope of the complexity of the systems that they work with. But so anyway, so we're going to try to integrate a little bit of this reasoning here in computer science, and yeah, so that's what I wanted to say. So the study of dynamical systems is really at the heart of what they do in Kybernetics, and this kind of reasoning, of way of reasoning, is also at the heart of their discipline. Okay. So, as I said in the beginning, we used to name this course Mathematics for Intelligent Systems. Yeah, so we are reviewing the requirements, mathematical requirements, for a deeper understanding of one, machine learning, robotics, and a little bit of computer vision. And so these disciplines answer things like how can we, so this use mathematics to answer questions like how can we represent the system, how can we represent the task that the system is solving. That all has to do with defining the problem. And then how can we solve the task, which is already using reasoning, the mathematical reasoning, in order to produce a solution for solving the task that we have at hand. And how can we characterize the algorithmic solution? So that's really kind of the guarantees that we will have at the end. Okay, so that's basically what this course is about. Now, I'm going to talk a little bit about mathematics in general, give an overview of mathematics, tell you what we're going to focus on in this class, because, of course, it's not in 10 or 12 lectures that we're going to view the entire mathematics. We're just going to scratch the surface of little islands. And we're gonna, at the end, see some examples. So let's dive into mathematics. So the question is, what is mathematics after all? So this is something that is unclear. Like the definition of mathematics is unclear because people have conflicting definitions of mathematics in general. But I think everybody would agree on what are the topics that are studied in mathematics. So the first thing that we all struggle with as children is the notion of numbers, quantities, and structure. So that's in algebra. So how do abstract sets kind of interact with each other? That's the key notion in algebra. Oopsie. So space. This is the study of geometry, and so how, we will see, hopefully in a better way than last year, differential geometry this year. And I suppose none of you have seen differential geometry, but it's kind of the study of surfaces and their abstraction to higher dimensions. And this is especially relevant for machine learning and robotics because they are used, and computer vision as well, actually. They are used all over the place in these intelligent systems, either to model the parameter space of the neural networks or so on. We talk about a manifold, or the actual output. So you're predicting, you're doing structured prediction, you're predicting an image, you're predicting whatever, like the position of a human. That's a manifold as well. So the parameter space is a manifold, the output is a manifold, the configuration space is a manifold. I don't know, a lot of things are manifolds. So not knowing what a manifold is really problematic, I find. So then and change, which is, analysis. So derivatives, gradients, Hessians, and all this stuff. But as I said, there's no consensual really definition of what mathematics is, and you have to go through kind of see what mathematics studies. And so depending on what bit of the mathematics corpus you're working on, you will have a different notion of what mathematics is. But for us, of course, as engineers, the mathematics is more like a language that allows us to model what the problem is in a very concrete or abstract and concrete way, and through that formal definition, come up with solutions. Okay, so I put the link to this video. I think it's kind of cool. So you get in 5 or 10 minutes, you get what is the entire mathematical field, and we can start going through this, and I will highlight the parts that we're going to work on. So the first thing that you should get from this map is that there are two parts. So there's the pure mathematics and the applied mathematics. Of course, there's the foundations here. We will talk about both things some things on both sides of that map. So we're going to talk about pure mathematics and we're going to talk about applied mathematics. The foundations are actually very important in computer science in general because there's this, the theory of computation, which arose with computer science or just before computer science, and that gave the theoretical basis of computer science. You probably all kind of read about this P is not NP kind of complexity theory and so on. You probably all heard about the Gödel incompleteness theorems as well, which is very linked to logic and logic languages and computer science as well. But we're not going to talk about that because that's somewhat, well, of course, I mean, logic and so on can be part of intelligent systems, but that's not the main focus of this course. So we're actually not going to talk about the foundations at all. Briefly going to maybe touch a little bit sets, but we're not even going to talk about set theory. Okay, so then in pure mathematics we have all the number systems here, which is kind of like pushing the things that we see from school when we are kids. And we are going to talk about, maybe we're going to talk about quaternions a little bit. That's the thing that I want to introduce this year. So talk a little bit in a deeper way about 3D rotations, because that's very important for robotics and computer science. And to some extent machine learning as well, because if you're working on a task where you have to predict some 3D orientation, then the output representation that you want to use is really dictated by your understanding of like SO3, and that's kind of, that also relies on your understanding on quaternions. But that's basically it. Maybe we talk a little bit about quaternions. We're not going to talk about that. So then there are structures. So we're going to talk about that a lot. So that's matrices, linear algebra, and so on. They are so fundamental to many things that we do, including modeling including when we are going to talk about optimization here. So the end of the course is about optimization. So when we talk about that, we model the local structure of whatever surface we're optimizing, which is also manifold, by the way. So the local structure is going to be modeled by some linear algebra objects like the gradient, the Hessian, and so on. And then maybe we decompose the Hessian, maybe we do an SVD, and so on. So these things are really in the structure, linear algebra, and also group theory, which is like, for example, SO3 is a group. So you need to understand group theory as well. So we're going to talk about that. We're not going to talk about combinatorics. Suppose, I mean, if you're coming from computer science, maybe not in electrical engineering, but that you've seen enough combinatorics so far. So we don't need that. What I said is we're going to talk about differential geometry, and I want to refactor. Maybe we'll have a guest lecture actually to do that. But not talk about so much about topology. We're going to talk about geometry, of course, especially with the link. So it's connected to algebra, of course, as you can model space by algebraic structure. That's like the basic thing in actually what we're going to see. We're going to talk about vector calculus a little bit, and that is because we need it in optimization here, and calculus, 3D, actually high-dimensional calculus. Differential equation we're going to talk about, but we're not going to see that. And then in applied mathematics, we're going to talk about probability theory, define what probabilities are. It's very fundamental for machine learning. We're going to talk a little bit about machine learning throughout the course. Like, for example, we're going to see backprop, which is so backprop is just a recursive application of chain rule. So we're definitely going to see chain rule when we talk about calculus and so on. And that's it. We're not going to talk about so much control theory or anything. Or game theory, we're not going to talk about that. But that's it. I think we went through all the stuff that we're going to see or not going to see. So if I want to summarize, we're going to start with some structure, so algebra. Then we're going to talk about geometry. Then we're going to talk about vector calculus, and so we're going to go there. And then we're going to talk just briefly about probabilities and then go to optimization. That's basically only what we're going to see. Many things we're not going to see. Okay, so of course, many mathematical courses are proof-oriented. This one is not. We're going to see some proofs sometimes, but it's more like sketching the proof or deriving, like a little derivation, which ends up actually being a proof. But we're not going to see so like fancy ways of proving things. This is not a pure mathematics course. This is more like, as I said again, so leveling everybody, having most of the definitions there, presenting the basic ideas of things like eigen decomposition, SVD decomposition, yeah, like applying chain rule, like making basic derivatives in vector, valued functions, and things like that. So what I want to say is like, just, we need to understand what is a proof. And we need to have, just so that everybody's clear of what I mean by proof, even though you should probably have seen many of those. So this is something that maybe some of you saw very early on when you were maybe 5 or 10 years old or whatever. It's the proof of the Pythagorean theorem. And anybody can understand that, including a child, a very young child, because it's completely graphical. So, I mean, that's one proof, okay? So, on this proof, basically, what you have is a decomposition of the square in 5 different things. So you have 4 triangles that are the same. At least when I say the same, it means that they are maybe isomorphic or something like that. So they have the same angles, and you can rotate and translate one and then match the other. That's what I mean. So the triangles have a little side of A and a big side of B. And, so that's, these have names. So that's like the hypotenuse is of size C. And what is that? The opposed and the adjacent side or whatever. I know these things in French. So, so we decompose the square like that. We can decompose the square with the same shapes like that. So I'm just sliding the things around, okay? So I took this thing, I pushed it here, then I took this, this stayed here, I took this one, and I pushed it here. And then I had something here, and I slide it over there. And now I identify what I have. I don't have a white square anymore inside the other square. I have 2 little squares, and I can just identify the surfaces. So how big is the area of each of these things. And from there, I have completed my proof. So I just have to basically identify that the white area is just the same, right? Because the shapes the colored shapes that I had inside remained. I just moved them around. And so I can just say that C square, which is the area of the big square, is equal to the area of the small square, which is A squared, and plus the area of the medium-sized square, which is B squared. And that's basically the Pythagorean theorem. So most complicated proofs are things that are, I would say, unintuitive. So if I told you originally what is the relationship between that and A and B without the square, we would never know. I mean, this is like completely unintuitive that it would be the square root of A squared plus B squared. And that's what mathematics gives us. It gives us facts that are abstract, true, and unintuitive. So if I tell you that 2 plus 2 is equal to 4, that's intuitive, that's maybe not interesting. But if I give you the Pythagorean theorem, and then you identify that there's one of these a triangular rectangle, whatever they're called in English, in your problem, boom, you can tell me what C is as a function of these 2 guys. because somebody did that proof. And so most complicated proof work this way. You have to basically construct something that goes beyond that little shape that you're looking at, identify something around that construction, and then come back to the original shape. And yeah, so that's just what I wanted to say. So that's why mathematics are very important for intelligent systems. It's because of this notion of this collection of unintuitive facts that you can just pull here and there once you've defined your problem mathematically and very concretely, okay? Of course, if you had to prove every crazy theorem along the way every time you want to reason about the system or make guarantees about the system, it would be pretty tough. Okay, the other thing, of course, that's super nice about mathematics, beyond the fact that it's a collection of unintuitive facts that are just given to you, is that they are true no matter what, right? So like the Pythagorean theorem, there's a version of, the Chinese version of it that has been found, written down 100 years before Christ. So that's pretty crazy. And it has been discovered by the Arabic mathematician 700 years ago. So it's been discovered and rediscovered in different cultures all around the world. So it's not necessarily a Greek theorem, right? It's a Chinese theorem, it's also an Arabic theorem. It doesn't really matter. It's true everywhere and always. Okay, so what is a mathematical problem? And there are two kinds of problems. But it's one that can be represented, starting to be actually really cold next time, analyzed and solved. So again, it's this thing where we build a definition of the system on using mathematics. We analyze it using mathematics, and then we solve it using mathematics. We characterize maybe the algorithmic solution to the problem using the methods of mathematics. That's what a mathematical problem is. And there are two kinds of problems. So there are real-world problems, and let's see some of them. So, for example, you would have, how long do I need to reach America if I'm traveling at 30 kilometers per hour? So that's kind of the typical child mathematical problem that we give when we are in 5th grade or whatever it is. How fast do I need to go to leave the Earth orbit? Already so that starts to be more involved. Okay, so I have to reason about the math and the physics of the problem and so on. And it turns out that it's actually super fast, that you have to go I don't remember, 17,000 kilometers per hour or something like that. What is the shortest path using highways between Stuttgart and Berlin? So this is something that we see in computer science a lot. You can model the problem by having a graph, and then you have the connections between, or the edges between the graph that are associated with a weight, and then you use an algorithm that's called a Dijkstra algorithm, and that solves your problem optimally. Or you can use a heuristic, and that's A-star, that was invented in the 60s for robotics problem, navigation. So these are real-world problems, but there are also abstract problems. So first one I could list is, what is the volume of the 5-dimensional hypersphere? So what's cool about abstract problems is that, just like the Pythagorean theorem is just a solution to an abstract problem, is that they lead to theorems. So it's not only that you're solving this for a particular numerical instant or whatever happens in the real world, you're solving it for all instances of this thing. So you define the mathematical object, here the 5-dimensional hypersphere, and you're looking for the volume as a function of some variables, which here is just the radius of the hypersphere, and boom, you have it for all hyperspheres of dimension 5. Okay, another abstract problem. Is the real part of any non-trivial zero of the Riemann zeta function equal to 1/2? So that's a $1 million problem if you ever solve that abstract problem, or if you had, because it's solved. So I think the answer is yes, I don't remember. But it took like 100 years for people to actually come up with the solution to the answer to that abstract problem. And the proof, I don't know, it's probably insanely crazy. I don't know. And then, so this was a conjecture, I think it's called. So this is something that, who did this conjecture? Was it Riemann? I don't know. You can look it up on this YouTube video, which is super cool. It has all sorts of graphical things, like it's really a cool video. I watched it like last year and I would watch it again. It's really nice. Anyways, so an abstract problem can be super well defined actually and involve many mathematical objects. It's still an abstract problem. Another one would be, which is another one of these problems that arose from, I'm blanking now. This was this German mathematician that at the beginning of the 20th century came up with like a list of, it was the program, whatever. So that was one of these problems, which was a little bit easier, I think, than this one, and got solved faster. So that's what the real mathematicians are working on, these types of abstract problems. They are not working on these real-world problems. These, I would say, are more engineering problems that, I mean, if they increase in complexity, they become these tough engineering problems. They might be just as tough as solving for an abstract problem, but they don't have the same impact. If you solve an abstract problem, you're solving something that people can use kind of like forever. Well, maybe if you solve an engineering problem, you already have really good solutions that can last forever. Yeah, it's like, for example, like the people who worked on the A-star algorithm, which is probably still used in many of the software around the world, were looking for a practical solution to a problem. And it turned out that they kind of abstracted the problem enough that it became kind of an abstract problem, I would say. So it's not that there's this clear divide. Okay, so now what we're going to do, as I said, for us, for engineers, mathematics is mostly a language by which we formalize problems, we define the structure of intelligent systems, and we try to give guarantees to our systems, or we find algorithmic solutions based on the math and so on. So, first thing we're going to do today is just go over language things about mathematics. So there are mathematicians that have invented a bunch of symbols to make that language usable. And we're going to go over some of these symbols. It's very important because that's what usually computer science people lack of, is to really have a clear picture of what the mathematical language is. And so let's go over some of these things. So if I want to list a bunch of elements, of course, we have computer languages, and they are in some way formal languages as well. But in mathematics, we have a specific way of defining lists of elements. So if I have an unordered set, I'm going to use these curly brackets, or mathematicians would use these curly brackets. And here we have two sets. We have x and y, and the little x's and the little y's correspond to elements of the set, which is usually written as a capital letter. So x with a capital letter means the x set. Little x means the element of that set, and we index the element 1 through n, for instance, to say that we're talking about an element, element I or element 1, 2, 3, n, whatever, of that set. If the set is ordered, meaning that the order of the elements matter, we would use regular brackets. And if it's only a pair, well, it would be as well brackets that we'd use. So here I introduce the Cartesian product between the set of real number, and that's also written R squared. Okay, the Cartesian product means that it's kind of all the elements of R, of the real numbers, with all the elements of the real numbers, so squared. So yeah, so that is that if we do the Cartesian product repeated n times, we'd have Rn, and these are the natural numbers, so 1, 2, 3, 4, 5, blah, blah, blah. Z is including the negative numbers. Maybe, I hope I'm not saying something wrong. I hope it's not with the, no, Q is with, yeah, the fractions, okay. Mappings from set to set. Right, so, okay, mappings can also be called functions in some context. So we are mapping something from the left side, we're mapping it onto something on the right side. So if I'm mapping a set to a set, be careful. We define it this way. The arrow, look at the arrow. So the arrow is just a regular arrow. If I'm mapping an element to an element, then I'm going to have here this little bar here. So this is typically the type of things that computer science students don't master at all, and you make mistakes. And then if you're writing a kind of paper where you don't formalize your system in a mathematical way, you're going to make mistakes. It's going to induce ambiguity in the way that you're describing your system. Eventually, people are not going to understand you, and so that's bad. So again, mathematics is a language. Language means that you're communicating to someone on the other end, that you want to convince, who you want to convince that your solution or the guarantee of your system or whatever makes sense. So be careful with these little details here of the language. Implicit argument. So these are these dots here. So this is saying that we have a function here. Actually, here this is the inner product that could take in whatever argument, doesn't matter. V is often used here for a vector space, which we will use a lot next week. So vector and matrices. So in this lecture, so vector and matrices are written in specific ways. Authors have all sorts of different ways of doing that. In this lecture, I'm going to try to stick to the convention that's in the Mathematics for Machine Learning book, which is used a lot in intelligent systems in general, which is that vectors and matrices are in bold. So it's a vector X. So here you see there are elements X's that are not in bold. So in my convention, or in the convention of that book, typically that would mean that this is a scalar and this is a vector. A vector, I think all of you are familiar with the basic notion of what a vector is. Basic notion is just like an array of numbers. We will see that that's not the definition that we will use here. We'll go a little bit beyond that, which is basically that vectors are elements of vector space, and then what is a vector space, and we'll define what a vector space is. Matrix is the same thing, but in a capital letter. So it's also bold. So it's not a set like these guys. It's bold. It's a capital letter. Yeah, it's a matrix. Okay, so that was for just basic stuff. So now, if we are talking about logic operations in our paper or in our derivation or in our description of the system, whatever, what we would do is use logic, and the first thing is to have clear the symbols that go along with propositional logic. So first thing is conjunctions. So that means something and another thing has to be true or is true, and that's the symbol here. Disjunction is the equivalent of or, so one is true or the other, and that resulting proposition is true. So it's the kind of the V sign, the opposite sign. Implies, so if a proposition is true, then the other will be true. That we use this arrow here. People are usually familiar with that. If and only if, the equivalence between propositions is just a two-way arrow of the same type, this double arrow. Elements. So I think usually people are familiar with that. So for all there exists, right? So that's talking about elements. So for all the elements in that set, then that proposition is true. Or for all elements in that set, that proposition is true, and I would use the conjunction, and that other proposition is true. Okay, so if we want to define a specific set, which happens a lot in talking about intelligent systems or machine learning or whatever. The idea is you have a set of things. For example, A is the set of elements in X that is strictly larger than 2 and different from 6. That's a perfectly fine way to define a set. But with all the symbols that we've seen so far, we can just define that in a more concise way using the language of mathematics, or the symbols of mathematics. So that's the exact same thing written with mathematical symbols. So we have that X, A is equal to the set, which is the curly brackets, of x's in X. The bar here would be translated in language as such that X is greater than 2, then we have the conjunction operator, and X is different from 6. So that's how we define that. And that's another perfect way of defining that. So say A is equal to the set of x's, such that, and then you put the for all x is equal to x is in x at the end. So instead of having it in the set definition here, you have it pushed in the conditions here. Okay, so this is just like combining all the mathematical symbols that we've seen so far to define sets. And I would go over one last thing, which is the derivatives. Symbols, usually you're familiar with that. It's like not rocket science either. So there's the derivative of x with respect to x. There's a total derivative, partial derivatives. So we will, of course, see a lot of what I'm talking in more details in these lectures. But it's important to note that these are completely different things. So total derivatives means that you're taking all the inputs that potentially depend on x and compute the derivative also with respect to those, apply chain rule from all the input variables. And partial derivatives means that you're only deriving with respect to that particular variable and not applying chain rule basically all the way to all the neighboring arguments. It's the partial derivative. We'll see that in detail. The Newton notation. So when you see dot here, this means that you're deriving usually with respect to time. And it's, if you have one dot, it's the first order derivative. And if you have two dots, it's the second order derivative. If x is position, which is usually an intent in the Newton notation. Then first dot means a velocity, and second dot means acceleration. And third dot means jerk, and fourth dot means snap, and fifth, I don't remember. Okay, so gradient. We're going to talk about that, and that's like, I saw some exams where people really didn't get that down really well. And I was a bit, okay, you shouldn't take the exam if you don't understand that notation and so on. At the end of the lecture, if you don't get that correct, it's very likely that you would fail the exam. So why? Because the end of the lecture is about optimization. It's kind of what we are trying to work towards and really nail all the parts. So like, okay, what is the Jacobian matrix, the Hessian matrix, how, I said this in the beginning, how can I decompose the Hessian matrix, blah, 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 so on, like really get all the parts right. And the gradient is like the most important part. So very important. Like know what the gradient of a function is, and Jacobian as well. Hessian, just the matrix of second order derivatives, partial derivatives. Integral, so the sign for integral, you've seen all of this in high school, whatever. So yeah, optimization. So the minimum, we write the minimum of a function. Okay, so pay attention to that. So that's used all over the place in intelligent systems paper. There's a difference between writing min x in x of f of x and writing arg min. The difference is very basic. Min gives you the value, right? So if I say the minimum of a function is a certain thing, that minimum means the output value of the function. So let's say I have a function like this. The minimum is here. When I say minimum, I'm looking at what is the value here, the height of the function. Argmin is saying here, what is the argument at that minimum? What is the value of the argument, okay? So that's what argmin is. So it's a y, it's not the x. Argmax and max, they're just, it's obvious. It's just the reverse. Okay, so final kind of piece of mathematical thing used all over the place. The way to define an optimization problem. We have minimize. That is saying, so that's not anymore for defining a set, okay? That's for defining a problem. So the problem of minimizing a function x, x is a function of x, sorry, f. So x here is saying x is the variable, the input variable, or the thing that we are looking into. So we are looking to minimize f over the x's. So f could have like another argument, for example. It could be f of x and y, and we'd say we minimize with respect to x. We'll see that in the dual problems things. Okay, the other thing is here, subject to. It's saying that we are minimizing the function f of x, but we want other functions to be true. So we want that these guys, these are called equality constraints, usually named H. So these say that at the optimal solution, they should be 0. And these are called, G's are called inequality constraints. And the fact that we have these guys here explicits that we have M and P of these G and H functions. So we have M equality constraints and we have P inequality constraints. Another thing that people are unclear about is the notion of closed-form solutions. So closed-form solution means that you can express the solution to your problem by only kind of basic operations, maybe basic functions, constants, but that you're not involving some kind of algorithmic tool inside of that, which would be, for example, like the summation over an entire set or something like that. And you're not taking the limit, of course, in the infinite. That would not be a closed-form solution. So the one that you're all familiar with is that if you have a polynomial of the second order, which is this thing on the left side, here it's just like a scalar, okay? So you're all familiar with that. Depending on the sign of A, you will have either something like that, or you will have something like that. It's called a convex function, and it has two solutions. So if I say, okay, what are the roots of that, which means what are the x's for which the polynomial is equal to 0, it has two solutions because it means that it crosses the axis at 2 points, and these 2 points are characterized in closed form by this guy. That's a closed form solution to the quadratic roots. A geometric theory, I think people are not so familiar with this result, but it's kind of a classic thing. There's a closed form solution to this infinite sum here, and it's just 2x. So that's like very useful for in computer science in general. If you suddenly identify, wow, we have an infinite series here, but it has a closed form solution, trying to approximate this by a very large n is going to be somewhat linear, and this is going to be constant and much faster. Right? Quadric programming, so that's like something that we will see. So we have the optimization kind of scheme that we saw with an equality constraint, and we are looking for the minimum subject to this equality constraint here. And it turns out that it has a closed form solution, which is quite complex, but it's still a closed form solution. Another closed form solution that is very important throughout machine learning, computer science, and so on, is the closed form solution to the regression problem. So if you have a bunch of data that is thrown to you on the plane, kind of like linearly, and you want to fit a line through that, then the closed form solution is to put all these points in a data matrix and compute the pseudo-inverse of the data matrix. Boom, you have your solution. So there's entire books written about this problem, but how to regularize, blah, 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 and the variance and bias ratio and all that stuff. But it's very important to know that in the basic case, linear regression has a closed form solution, which is the pseudo-inverse, and we will talk about the pseudo-inverse in 2 weeks. Okay, so now I'm going to talk about 3 examples, and then we can call it off. These examples are just there to kind of shake your brain about what the content of this lecture is going to be. You're maybe not going to understand exactly what's happening, but it doesn't matter. It means that this is where we're going, and that should motivate you to want to understand the content of this lecture. The first one, well, actually, then that's 4 examples, sorry. But the first one is not really an example. This is more something that I want to talk about in terms of, again, making the point why mathematics is important in intelligent systems, and that's the curse of the dimensionality. I want to talk about that. So it happens over and over and over again, machine learning, robotics, all over the place, in algorithmics, in AI, all over the place. This is the idea that when you have data, or you have a solution, or you have something that is of high dimension, many algorithmic solutions break down, and due to the curse of dimensionality. The idea was coined by Richard Bellman, I think in the 50s or something like that, at MIT. And so it's found in so many domains. This just was kind of like mentioning the domains, numerical analysis, sampling combinatorics, machine learning, data mining, databases, motion planning, etc. And it occurs, in these things. And it's a little bit unintuitive, and that's again an example of what mathematics is good for, which is thinking a lot about an abstract problem, eventually coming up with an unintuitive fact about the problem. And that's what it is. So it has different forms. So the curse of dimensionality. One way to see it, and this has to do with nearest neighbors. Why nearest neighbors breaks in high dimension? So nearest neighbors is a thing of statistics, of machine learning, or whatever. It's a typical technique. It's saying, I have a bunch of data, and the way that I'm going to represent that data in a function is, so that the data is a training set and in machine learning. And then I want to generalize to some test, validation, real-world application. On the training set, I'm going to fit local models, and I'm going to give you the value of that particular neighborhood of the data set. So let's say I have a data set that's like pockets, like I have 2 inputs, so it's like something on the plane, and I'm trying to do a regression task, and I'm going to give you the output for that based on my training data. I'm going to tell you so 2 output that maps to 1. So like, for example, it might be where you are in this room, you guys, and the output might be your height, right? And I would say like the distribution of how you are is somewhat makes sense in terms of your height. The closer you are, the smaller you are. The further you are, the bigger you are, maybe, And nearest neighbor would be, I would pick like randomly a point for test time, and I would check out what was the height of the closest data point that I had, and I would give you, that's your height. So the inputs there are only 2, because it's kind of planar problem. Where nearest neighbor, so hopefully you understand what nearest neighbor is now. Where nearest neighbor breaks is when the dimensionality of the input is super large. So if I start to say, or not even super large, just a little bit large. So if I start to say it's not only about the position, it's also about what time you got up in the morning, what did you have for breakfast, which is maybe out of like, So I include like out of like the features, I start to list many features. Maybe I have 10 of those. And I take the nearest neighbor with respect to these features by computing the Euclidean distance with respect to these features. It's going to break. And so the idea why it's going to break, it's going to start really answering complete garbage, even if the data was correlated. And the idea is that the fraction of the volume of a P cube, so that's the idea here, covered by a subcube of size, side length, distance is plotted here as a function of the dimensionality of the problem. So the 2 example was the one that we were talking about. So the fraction of the volume of the entire cube here, of the unit cube, given by one of these neighboring cube in the 2D case, so this would be a square, increases. So as a function of the length, and you see how it increases. So basically, for a side cube of, for a cube of side length 0.4, which would be around here, in the 2D case, so on the plane where it's a square, I would have 20% of the volume of the hypercube covered. The thing is, in 10 dimensions, in order to have 20% of the volume of the hypercube covered, I need to have a side length of 0.8. which is basically I'm covering the entire range here, which means that subcubes in high dimensions are not local anymore. They cover the entire space. And that's the reason why nearest neighbor breaks. It's because you then have to consider every instance. So if you guys are my data point, all of you are global to the feature space if it's in high dimensional feature space. You're not local anymore. There's no way to kind of say that you generalize locally to your little neighborhood. You have to generalize to the entire thing, and it's impossible to basically use like a proper Euclidean distance thing to reason locally. Okay, so that's one aspect of it. For the sampling-based case, and they're all connected in some way, but for the sampling-based case, you might think of the ratio of the high-dimensional sphere with respect to the high-dimensional cube. And as P grows, the ratio tends to 0, which means that the hypersphere inside the hypercube covers 0 volume, like snaps, like covers nothing compared to what the hypercube is. And that's going to be a problem when you're sampling. And for example, when you are sampling configurations, what happens with the curse for motion planning, what happens with the curse of dimensionality is that you basically only sample on the shell. So if you look at how the sampling are distributed, all the in high dimension, like 10 or something like that, all the samples are biased to be, if you sample uniformly all the dimensions, are biased to be on the shell of the hypersphere. And that means that they are kind of all at the same distance to each other. And you lose this notion of neighborhood again. So there's really this notion that if you rely on Euclidean distance in high-dimensional space, what this distance is giving you is basically garbage in many of the cases that you are interested in. So everything is kind of at the same distance as everything. So you can see this by thinking, if I have a 10-dimensional vector and I sample randomly another 10-dimensional vector, and I compute the distance between these vectors using Euclidean distance, what happens is that there's always kind of two features that are kind of close to each other and others that are not. And that means that the average distance that you get between random vectors is kind of always the same. That's the same concept as saying that all random samples will end up on the shell of the sphere and there's no samples in the volume, because you will always have kind of a feature that will push you on the, randomly, that will kind of like push you on the sphere. That's kind of like the intuitive notion. Anyway, so it's hard to get this unintuitive concept in your head. I even have a hard time just explaining all of that. And that's where math, actually reasoning mathematically with equations, will make unintuitive things more clear. Okay, so I think I'm running out of time, so I want to kind of skip this. So this is just, I mean, you can look at it on your own time. This is just saying like the consequences of the curse of dimensionality. The basic idea, you need exponential time, exponential samples, exponential data points in machine learning with higher dimensions. This is just... So what is also difficult is to see when the curse of dimensionality arises and when it doesn't. So that's like also the non-intuitive things, because sometimes you think, oh, it's a high-dimensional problem, we are going to hit the curse of dimensionality, and it turns out not. So it really depends. Okay, so now these three problems. The first one is the PCA, the principal component analysis. So who has seen PCA before in some class? Just one guy, so a show of hands, maybe 2, 3, 4, the little hands. I saw just the P of PCA. Okay, so yeah, so I guess some of you, the idea of PCA is to, if you have data distributed in such a way, is to basically capture the entire data set using maybe the mean and capture the covariance in a way that's like just a minimal set of vectors. So you have all these data points, and you reduce your data set by just in which directions is the variance kind of distributed, or yeah. So the way you do that, so you're given a data set of vectors. So now you see these guys are in bold, so that means that these guys are vectors. So the principal components are just an ordered set of vectors that are orthogonal to each other, and that best fit the data set measured by the mean squared error. These vectors constitute an orthonormal basis. We will see what that is. We'll see that what orthogonal means for vectors. Principal component analysis is the fact that to retain only few of the most informative dimensions, and it can be shown that the principal components are eigenvectors, so we'll see what eigenvectors are, of the data covariance matrix, which means that we can attain them by eigendecomposition of the covariance matrix, or, in a more direct way, by singular value decomposition of the data matrix. So that's the algorithm resulting from the SVD view. We'll see what the eigendecomposition is and the singular value decomposition is. But basically, you compose the data matrix, which is a matrix where, so by the way, that's the way to write the set of matrices. We'll see that next week. But basically, X is a matrix where we have the vectors as, I think, column vectors. Yeah, so each data point is a column vector in the matrix. Then we compute the SVD, the singular value decomposition. It's a decomposition that transforms the matrix in 3 parts. The left singular vectors, the right singular vectors, and this most important part, the sigma matrix, which is a very sparse matrix containing the singular values. We'll see that in all details in 2 weeks, I think. Yeah. Then we sort the eigenvalues, which are in this case the squared of the singular values. We'll see why. It's only in this case. It's not always the case. And then we truncate the top m eigenvalues and reconstruct the data matrix in this way. And yeah, that's basically the that's it for PCA. So note that that's why we can do the eigen or SVD. Since the empirical covariance can be written in this way, the squared singular values of X are the eigenvalues of S, and then it follows that S has these actual structures based on the SVD of X. We will see that, not PCA in detail, we'll not see PCA again, just we will see the mathematics behind PCA. Another problem I wanted to talk about is trajectory optimization, which we'll see in more detail. Philip will probably do it next year in the second part of the semester. So what is trajectory optimization? It's a cool thing from robotics where this is from Willow Garage in 2009. It was a startup in the Silicon Valley that lasted for 5 or 10 years, I don't remember. And they basically had 30, 50 people working like mad, creating ROS, which is still used today. So it's an open source framework for robotics. And then they also created a PR2, which we have one in the lab, but it's kind of out of order. And one of the main problems in robotics is motion planning. So trajectory optimization is a way to kind of smooth out trajectories. So that's a completely unsmooth trajectories, and optimization would smooth that out by constructing an ordered set of configurations. So that's vectors which describe where the robot is in space. And the optimization algorithm is to minimize the smoothness or maximize the smoothness of the trajectory. That's a penalty on non-smooth trajectories. So that objective term penalizes these wiggling things, subject to some inequality and equality constraints. And yeah, so the inequality might be like obstacle avoidance, and the equality might be something like goal set, like to really reach B or whatever. And A defines an inner product. We'll see what inner products are based on the vector representation of trajectories. So the algorithm is going to work this way. That we'll see at the end. That's optimization, so we'll see at the end. So we basically have a simple problem with only inequality constraints, and we can solve that with augmented Lagrangian, where we basically add to the objective two terms. We add the constraint, where that is multiplied by some Lagrange multiplier, and we add the squared constraint. That's how augmented Lagrangian optimization works. And then we solve the unconstrained problem by taking the second order Taylor expansion. We will see what that is. It has basically a first order term, which is just the gradient of that function at that point, and a second order term, which is the Hessian at that point. That's the second order Taylor expansion. So it's second order because 1, 2. And we set the gradient with respect to the perturbation here to 0. That gives us an update for a step to take. That's called a step in optimization. Maybe we do some step search, whatever. We don't get into these details of how to set gamma here. It's the step size parameters. We will see how we can do that in one of the last lectures using line search, sorry. And that's here, that algorithm here. This is called the Newton method for optimization. So the way to derive, the way to go from here to here, the way to go from here to here, that's called the Newton algorithm for optimization. We will see that in detail. And then you update your Lagrange multiplier and you go back to 1 and you optimize. That's the optimization procedure. Final example, the Kalman filter. Who has seen Kalman filter in class? 1, 2, 3, 4, 5. Okay, a lot of you. Okay, so the Kalman filter is something to estimate the state of time-invariant linear dynamical system. Time-invariant means that the dynamical system doesn't change over time. And it has the following description. So it has A and B explicit the dynamics of the system, which means so X is the state of the system, and B is the control matrix, A is the dynamics matrix, and they express the dynamics of the system. So if I input a control on the system, how is the state going to evolve? And then C is the observation matrix. So it's saying if I have a particular state, what is the linear combination of the state that will produce the observation? And so that characterizes my observation process, and that characterizes my dynamics, the dynamics of the system. It's all linear. Linear, we'll see also what linear means, but it basically means that it's a bunch of vectors and matrices. That's what linear means. Or constant matrices. So yeah, the Kalman filter produces a state estimate. X hat given observation y, controls u, the system's dynamics A and B, and some noise prior that I don't talk about here on these w's. So how the Kalman filter works is by having prior knowledge here of the system and measurement. And the prior knowledge is going to be used in the prediction step in order to produce some prediction of how the system is evolving using the dynamics and the control. And the measurement is going to be used together with the prediction step to update the system and produce what we think the output estimate is. And then this is going to feed back into the kind of state that the estimated state that we have at that notion. And we're going to go again with some new observation of the state and measurement. The whole goal is to estimate the state of the system. There's a very strong assumptions on the whole thing. So the dynamics of the systems are linear. The distribution of the state and measurements are Gaussian. And the observations here is also linear. So it's a pretty highly constraining setting, but we can linearize our systems. And so often we can use locally a Kalman filter because we can linearize the system. Okay, so just the Kalman algorithm is going to look something like this. We're going to have a prediction step, and where we update the covariance, we'll see kind of the update rules that we can apply to covariances of Gaussian distributions. That's in one of the last lectures. And here we compute the Kalman gain, so that's the update rule. Compute the Kalman gain and apply it to update the state. So here the gain is applied here, and we update the covariance associated with the state here. What's cool is that you can see the Kalman gain as projecting the observed residual, which is this part here. That's also called the innovation on the state space by minimizing the squared error measured by the empirical state covariance. And so that's actually a projection operator. And we'll see projections in 3 weeks. That's a type of linear operation that basically, if you have a point there, and projects onto some linear subspace of the vector space. And so we'll have a better understanding of these types of operators here, these projections operators. Okay, so I'm out of time, so I don't know how much I should conclude, but basically, yeah, so what I wanted to say here is that mathematics are used to derive abstract truths about abstract problems in general, and we can use that in the way we reason about intelligent systems. And usually the facts that come from mathematics are unintuitive. If they're intuitive, they're not so interesting. The interesting facts are the unintuitive ones that we can then leverage in our reasoning about intelligent systems. Yeah, so we cover a bunch of these concepts in this course. I think I highlighted enough, like what we're going to see, what we're not going to see. It is not a proof-based mathematical course. It's more like seeing a bunch of definitions and results, language tools, so that you can be better mathematical engineers. If you want to really follow well in this course, I'd suggest printing the book. It's available online. You can also order it like in a nice printed fashion if you want, but it's free, or you just have to print it. It's maybe €5. I think it's worthwhile. At least the first part. We're not going. So this book has actually 2 parts. It has a second part concerning machine learning algorithms studied in a mathematical way. We're not going to cover that, so you can just print the first part. That's the outline of the course. The slides are available online as of in 1 hour. I put them online, and I will see you next week.